other talk, so I'll share the slides. This will be the overview of the MVAPICH project, latest status and roadmaps. So let me is this visible?
Yes.
Okay. So in this talk, broadly, I'll be just like the previous years. I'll try to provide an overview of where we are heading, so that the MVAPICH user community can get an overall idea. As many of us know, I mean, we are in an exciting phase. If you take a look at like a 2017, we crossed 100 petaflops. In 4 years, we have come like the Fugaku, which is the 442 petaflops. And obviously, the community is heading into the Exaflop. And mostly, I mean, we are almost entering the end of this year. Either at the end of this year or the next year, we'll see the Exaflop system coming. So in general, if we want to design the programming models for these kind of exascale systems, so here we see all different programming models people are trying to use for HPC, big data, deep learning, etc. And at the bottom, we have all these technologies. Networking technologies, multi-core, many-core architectures, and of course the accelerators. And then up at the top, we have the different application kernels and applications, both HPC and DL. So how do we bridge the gap? So this is where the software architecture comes in. We typically have some kind of a middleware, and then we need to design the communication library for these programming models. Either we can do this in a layered manner, or we can also try to do the co-design. So this is a very high-level framework in which the community has been working on. So in our group, like the MVAPICH team is also following exactly the similar kind of an approach, trying to design MPI plus X at the exascale. Of course, there are a lot of challenges here. I mean, the basic performance to scalability to memory footprint, scalable collective communication. How do we balance intra-node and inter-node communication, because the nodes are becoming larger and larger with more number of cores. How do we handle efficient multi-threading, integrated support for accelerators, fault tolerance, QoS, support for hybrid programming model, virtualization, energy awareness. So all these are the open research directions. And especially MVAPICH project has been trying to address this as we have been going along. As many of you might be knowing, the history of MVAPICH, we started it almost in the day one of InfiniBand. When InfiniBand was introduced October 2000, we were ready. Earlier to that, we were working on Quadrix and Miranet. Some of you might have been remembering that. And we had the very first open source version of MVAPICH, MVAPICH1. It used to be called just MVAPICH. It was demonstrated at SCO2 2002, almost 19 years back. And if some of you were attending that conference, we had a really hard time even to run an 8-node InfiniBand, okay, in a stable manner. But now things have changed quite a lot over the years. The technology, the ecosystem, the MPI stacks. Now we can deploy 8,000 nodes kind of systems in a very easy manner. So over the years we have been working on. I'm very proud of my team. So we are like at 20 years and going steadily. The software stack is used by more than 3,200 organizations. These are our registered users. Just from our website, we have crossed like last week 1.43 million downloads. These just from our websites. Of course, our MVAPICH library is available with a lot of other software stacks, Red Hat, SUSE, OpenHPC, SPAC. We don't keep track of those. And it's also empowering many of the top 500 clusters. And we're also a partner in the 10th ranked TACC Frontera system and working closely with many of the end users to empower the top 500 systems in the last 15 years. So this one shows a very quick timeline, release timeline and downloads. As you can see, over the last several years, we are in a very upward curve with respect to the downloads. So this is the overall software architecture, and we call it like a software family. I'll introduce. We have a little bit different versions for both HPC as well as the DL and machine learning. So these are all the different kind of networking technology. We started with InfiniBand, but gradually we have been expanding to IOAP, Rocky, OmniPath, in AWS EFA. We are working with Rockport networks. You will be hearing a little bit later. I'll also mention about that. So we are trying to take advantage of all the features and mechanisms of the latest technologies and as well as the platforms both from the CPU, DPU, even the GPUs, both NVIDIA and AMD. And we take all these things and then trying to make sure that how we take advantage of the latest mechanisms to design this high performance and scalable communication runtime. So this is our MVAPICH team's the core research focus. We always come up with the best designs. We try to evaluate all the different designs and then see which design works, delivers the best performance. We have prototypes. And then in 6 to 9 months, we try to actually make it available in our MVAPICH2 library. So we go through a very rigorous QA procedure before making a release. We have exhaustive unit testing, different kind of all different platforms, interconnects, a lot of different benchmarks. Just like to give you an idea, we have almost like 200 servers continuously running all different kinds of tests. For every commit, we spend almost about 18,000 core hours to make sure that the code is stable. We also take care of performance evaluation and tuning, application-based evaluations, and evaluation on large-scale systems, and then we push it into for public release. So even our alpha, beta, RC1, and RC2, they also go through very in-depth testing. So we have a kind of a software family. We started with MVAPICH2, but as you know, the field is moving very fast with all different kinds of networking technologies, the drivers, operating system. So because of that, we have actually a little bit fragmented over the years. And I'll talk in the end, we are again trying to bring it back everything. So here I'll just go into where we stand. We have the basic MVAPICH2, and that also runs on Azure directly because they also use InfiniBand. Then we have an MVAPICH2X version. So there we have the MVAPICH2X and then MVAPICH2X AWS. This is the GPU direct version, both for NVIDIA and AMD. And then we also have the InfiniBand network analysis and monitoring, INAM, OSU Microbenchmarks. So I'll try to touch a little bit of each of these. On the basic MVAPICH2 side, we had the last release, MVAPICH2 236. So we recently made it. It has a lot of features. So let's take a look at some of the highlights. I'll try to touch base on some of the basic performance, internode communication, scalable startup. You heard about Gilad's talk about SARP, collective offload, and we are also working quite a lot along the direction of MPIT. So these are some very fresh numbers from AMD Milan systems with SDR200. As you know, the AMD Milan is the latest fastest system. So here we get like this intranode latency. You can see around 190 nanoseconds kind of things. Bandwidth, we are able to deliver very close to 22.3 gigabytes per second. Now, as systems are being deployed on very large scale systems, like the MPI libraries, there is always a focus on how quickly you do the startup. Okay? Because think of like a 500,000 cores. If it takes 1 hour to start the job, then you don't get good performance. So continuously, we have been evolving these. So these are some of the numbers we did with some of the enhancements we did in 234, and that is being carried out. So here you can see, this is on the TACC Frontera. On 4,000 nodes with 230,000 processes, MPI init just takes 31 seconds. Okay? Within half minute, we are able to finish the MPI init and get the thing started. And compared to other MPIs, you can see there is a significant benefit for MVAPICH2. Then as Mellanox/NVIDIA have been working on the SARP, we are trying to actually integrate it in a very tight manner with our stack. So these are actually numbers taken on the full scale Frontera. So if you take a look at here, like MPI already used, this is the maximum number of nodes, 7,861 nodes with PPN1. We are able to, this is the software-based solution, this is the SARP-based solution. So we are able to improve it by a factor of 5x, barrier by a factor of 9, and then also the MPI reduce by a factor of 6. So we actually presented the paper with all the detailed results. I think all these slides have a lot of reference to the publication. So if you want to know more details, please feel free to take a look at this paper. Now this is as the MPI libraries, as the systems are being complicated, people are trying to understand where I gain performance, where I am losing performance. So in this context, we are working very closely with the MPI-T functionalities or MPI tool functionality. It was introduced as a part of the MPI 3.1 standard. So we are working very closely with the TAO group to make sure that you can do very nice performance engineering. So that means instead of the MPI library being a black box, we can try to make it white box. So that means if your application is running, you should be able to exactly find out where the time is being spent in the MPI library, how much memory is being consumed. And based on that, you can actually do some analysis and you can actually control the different variables. So this is what the MPI-T has these kind of features. P-vars, you can take information from the library, and based on your analysis, you can dynamically change the behavior of your MPI library to 3 P-vars. So today, later, actually, Professor Samir Sande will be giving a talk, and then you will get to know more details on these features. So then some of the upcoming features I indicated, like we are working with Rockport Networks, so they will be giving a presentation a little bit later today also. So this is a new kind of a switchless networks. So we are trying to have a very tight integration of our MVAPICH2 with their network. So here you will see by appropriately using multiple queue pairs, in this case like a 4 queue pairs, we are able to reduce like not only the latency for like the large messages, we get like almost 3.9x improvement, but also have like a 4x and 4.5x improvement. The Rockport networks also has a lot of additional features. We are working with them. We have an initial release. In fact, 236 would be working, but we'll be trying to make a little bit of more formal release with additional features very soon. So then with respect to Java binding, a lot of people now started using also Java with respect to, in addition to the MPI libraries. MVAPICH2 didn't have that. We got a lot of requests. So we are trying to work on this. So here you will see the Java bindings. There are different Java buffers. You can have arrays or buffers. So we have different kind of designs. Here we are showing some initial results of a Bcast performance with 8 processes. So you can see using buffer APIs, we can actually give you very good performance. So tomorrow there is a short presentation by Dr. Amir Safi. He will present more on these. And obviously these are these solutions are being worked out, and very soon you will be seeing an MVAPICH2 Java binding support being available in the release. So this is another project we are working with Sandia National Lab. Some of you might have heard of SST. That is the Structural Simulation Toolkit. So the idea is that as these exascale systems are coming, you want to understand the dynamics of topology, the dynamics of different algorithms. So can we simulate the entire system? So this is where what we have done. We have done a tight integration of the MVAPICH2 with SST. So as you can see, let's say you want to have a question saying, okay, on a 4,000 node, I want to do all-to-all, how this algorithm will perform compared to a torus topology versus a dragonfly versus a fat tree. So using this integrated environment, you can actually try to get these numbers. You have an algorithm, you try to, it is actually running in the MVAPICH2 framework together with SST. You will get a simulation, and here it says, like, for example, the fat tree will give you the best performance in this kind of cases. So you can also try to utilize it for different algorithms, different topologies, different kind of SST also has a lot of cache simulation. So this is the kind of the newer direction MVAPICH2 project is entering, so that we can utilize not only just have the pure software which is running on the current system, but it can also be used to drive the next generation architecture. So there will be tomorrow's, again, there is a short presentation by Kausik, so he will be going more on this aspect. So then going to the next library, which is the MVAPICH2X. So here we have a lot of additional features. Over the last few years, we have added direct connect transport, cooperative rendezvous protocol, asynchronous progress, and XVM mesh clustering. So let me try to touch base on these. So this is where the DC protocol comes in. As you know, the RC, UD, DC are there. So with DC, as you can see, you get significant benefits, like a 76% benefits is a Neuron application, which is running on the EPFL cluster. There was a presentation in the last year MUG. You can take a look at that for more details. So similarly, a few years back, we designed this cooperative rendezvous protocol. That means when you have within the node, instead of like me sending data to you, completely can both sides come together. So that's why it is known as cooperative rendezvous protocol. And with that, this was a SC18 Best Student Paper Award finalist. And through this, you can see real benefits in the application. And this solution is already available in the MVAPICH2X many years. We also have a new asynchronous progress design that has also been there since MVAPICH2X 23RC1. So in this kind of a design, you don't need any additional code. Using the same code, you can actually try to do the additional asynchronous progress. And here we show some results compared to the different MVAPICH2 designs as well as the Intel MPI designs, and see you can benefit by 27%, 33% aspect. So this was also presented in the Parallel Computing 2019 journal. So then we have the XP-MEM support, as many of you know, that is the being made available with a lot of MPI libraries. We are the very first one many years back to get started on these. So here again, you can see this is like a shared address space based on 2 zero copy reduction. So we can try to do within the node, and especially now, since the number of cores are increasing, like a 64 core, 128 cores. If you take even a 1,000 core environment or a 4,000 core environment, a lot of communication happens within the node. Okay? So in addition to accelerating the inter-node capability, you also need to accelerate the inter-node capability. So this is where our solutions are being pushed, and they can work together with the inter-node based solution to provide you very good performance for these collectives. So then a lot of things are being worked out on the MVAPICH2X. This will be available in the upcoming release. We are trying to finish an MVAPICH2X release before MUG, but we couldn't finish it. Might be you will see the release next week. Some of these features will be there. The others will be there in the next release. So we have some optimized derived data type design, exploiting hardware tag matching, neighborhood collectives, support for the SARP streaming aggregation, and support for the AWS Cloud ARM instances, as well as the support for the Oracle Cloud HPC sets. So here are some of the results from the optimized derived data type. So here we have actually internally, we have worked on a lot of mechanisms to make sure for different kinds of data types, which mechanism to be used appropriately. Okay, and with that, if you see here, we have like an ASMG, and this is the WRF, and here you can see like almost compared to the basic MVAPICH2. Here we can give you like a 1.75x improvement compared to Intel MPI. We can give you 2.5x, and similar also for the NASMG. So there will be again later today in the short presentation, Kaushik will be going into more details. So this will be a design which will be coming out next. Gilad mentioned about the hardware tag matching. We also have the design. This was presented in the ISC last year. We have here it shows benefits like an MPI I all-to-all, that is a non-blocking all-to-all. With the tag matching, you can see like a 32 nodes, 64 nodes. We can show benefits up to like a 1.7x, 1.8x, etc. So then in the community, a lot of people have been working on neighborhood collectives. We had a paper here at Supercomputing 20. It is trying to show some results. If you can implement this neighborhood collectives efficiently within the MPI library, you can get up to like a 34x speed up. In this case, SPMM kernel, or even here like a NAS DT, you can get 15% improvement. So this is on our roadmap. We are trying to bring into the MVAPICH2X. So then with respect to the SARP aggregation mechanism, so these are some of the very recent results. As you can see, like this is the latest MVAPICH2X, and this is the next which is coming out. As you can see, with the SARP integration, we can have almost a benefits of 3x, 3.95x. That is all reduced. The same thing also is on the reduce. So once again, today afternoon, there is a short presentation by Bharat. He will go into more details on this. So then for the last several years, we have been working with all the different cloud providers. In fact, you will be seeing some of the presentations today. So especially, as you know, the AWS doesn't use InfiniBand, but it uses the EFA adapter, Elastic Fabric adapter. We heard about that in yesterday's tutorial from AWS folks. So we have an optimized version of the MVAPICH2X running directly with the EFA. Okay? And currently we have extended that design into their latest ARM cluster, the ARM instances. So that's what you see some here, sample numbers. We are comparing MVAPICH2X with OpenMPI. As you can see, with all reduced scatter, we are able to deliver better performance compared to the OpenMPI. Again, there will be another short presentation by Shule today afternoon, and he will go into more details. And since last year, we started collaboration with Oracle, with funding. So we have a very in-depth collaboration going on. We have actually officially not released, but there is a drop we have given to them. They are actually running it on their system. You will see a formal announcement coming out soon. So here it shows again an HPC 2 instance on the Oracle cloud compared to the other libraries. As you can see, like a Bcast, Reduce, we are able to give very significant benefits. Here you can see almost 21x benefit. Here it's a 2.7x benefit. Sule will again present some of the more detailed numbers in the afternoon. So then moving into the GPU side, as you know, there are a lot of actions taking place. So this is where we started with the MVAPICH2 GDR called GPU Direct RDMA. Gilad mentioned this when Mellanox and Mellanox and NVIDIA started this project, GPU Direct RDMA. We worked together with them to bring all these concepts together, and that also matched very well with the CUDA-aware MPI concept we had earlier. And this is how the MVAPICH2 GDR project started. And just last week, we made a new release. Some of you must have heard of this. We have a lot of cool features here. Let me go and then present some of these things here. So not only like we are continuing with the CUDA-aware MPI concept, I'll introduce very soon in the next slide. Earlier, we are supporting the NVIDIA GPUs. Now AMD GPUs are also being supported under the same MVAPICH2 GDR. And some of the new things we mentioned about that this last year MUG as a work was taking place, but this release actually has the support on the fly compression for GPU to GPU communication. We have optimized collective support for DGX on their system. And also through this MVAPICH2 GDR, we have been enabling the deep learning, machine learning, and data science with DASC. Yesterday, if you attended the tutorial sessions, you would have seen, I'll try to highlight some of those things also in the next slides. So as many of you know, this CUDA-aware MPI concept, in fact, from our group, we started, the very first paper was presented in 2011, almost 10 years back at our ISC. So the idea is that if I have a GPU, instead of doing CUDA mem copy and doing MPI send, MPI receive, and CUDA mem copy, especially if the GPU and the InfiniBand, they're sitting in the PCI bus, can the data transfer directly go from GPU to the network and network to the GPU? So in that case, the application developer, they don't have to write too many of these CUDA mem copy calls. They can directly say, okay, MPI send from this GPU buffer, and then MPI receive from the other GPU buffer. Then the MPI library internally will try to find out the correct path, the correct protocols, the correct thresholds, and will be able to give you the best performance. And in that context, even the code development becomes also highly productive. So with that kind of the GDR project, when we started with a CUDA our MPI, we also worked together with NVIDIA on the GDR copy library. So if you put everything together, you can see these are on the x86 system. You can actually have data transfer from GPU buffer of a node to a GPU buffer of another node in just 1.85 microseconds. Okay? And you can also get a very big boost in terms of the bandwidth and bidirectional bandwidth. And these are some of the numbers on the NVLink 2 and Volta system. So here you can see, again, GPU to GPU within the node, we can data transfer the data with only 760 nanoseconds. Internode is around 2.18 microsecond, and we can actually try to saturate even 60.548 gigabytes per second on the NVLink 2, and this is the internode bandwidth is 23 gigabytes per second. So these are some of the numbers from the Azure instance. Thanks to Azure folks for allowing us access here. This is their ND-V4 series. I think Jitin will be presenting from Azure a little bit later today. So here again, we are able to see the bandwidth within the node, internode GPU to GPU. We are able to, this is the latest MVAPICH2 GDR, we are able to give around 133.26 gigabytes per second. And then the bandwidth around on the internode side, around 23 gigabytes per second. So I mentioned about AMD GPUs. Since the GDR235 release, we have been supporting the AMD GPUs. So now with the same library, you should be able to utilize both the NVIDIA cluster as well as AMD cluster. So this is the ROCm aware MVAPICH2 GDR. And here again, we are trying to show these numbers from Corona cluster at Lawrence Livermore National Lab. And here you can see like some of the internode point-to-point. We are able to deliver at 1.75 microseconds, and internode GPU to GPU is around 3.99 microseconds. And these are some of the numbers we are comparing here with the MVAPICH2 GDR with the latest OpenMPI. And as you can see, like already used 64 GPUs, we are able to almost give very flat performance here, and also similar kind of things in the Bcast. So as this AMD ecosystem is picking up, I'll strongly encourage you to use the MVAPICH2 GDR latest version, and you should be able to get significant boost in your application level performance. So then this is the feature on the fly compression. So the idea is that, as you know, the GPU has a lot of, we have the CUDA-aware MPI concept I introduced earlier. So that means you can actually do directly communication from GPU to GPU. So then the question is, if I'm trying to send a large message, instead of sending the large message, can I actually do compression on the fly? Okay? Because the GPU has the resources, and if I can do that on the fly, then over the network, I can send only a smaller amount of data, and that gives actually the latency reduces. Of course, there's an overhead of compression, so there is a trade-off you need to take care, especially for large messages. We see benefits. And here, so this, the latest GDR236 release actually has this support, so you should be able to experiment with it. And here we have carried out evaluations of AWP ODC. This is a seismic simulation application. And as you can see, like with the different GPU kernels, the compression kernels, we are actually at the application level. You can see here, like with the 512 GPUs, we are able to boost the throughput of the application performance by 18%, here 128 GPUs by 35%, and similar things, we see the runtime reduction. So that means this actually gives you a very big boost in accelerating the application level performance on the GPU cluster. So then the latest release, we have also optimized it for DGX2 800 system. As you know, this has a lot of HCAs and all. Here, some of the sample numbers we are trying to show for all the collectives. And again, we are comparing with Nickel. As you can see, compared to Nickel library, we are able to deliver far better performance for messages of the smaller range, like up to 16K. And larger messages, we remain very similar to Nickel. And today, again, there will be a presentation, short presentation by Chen-Chun Chen, and he will go into more numbers here. And as we indicated in the yesterday's talk, through these MPI-driven solutions, we are trying to handle even the ML and DL training. So that means if you are trying to do any of your like TensorFlow, PyTorch, MXNet, etc., we have done a tight integration with Horovod, Torch Distributed, and DeepSpeed. We have a project called High Performance Deep Learning. You can actually go there, and there is a very nice user guide you should be able to download. And by together with the MVAPICH2 or MVAPICH2X, you can take care of CPU-based training. With MVAPICH2 GDR, you can do GPU training. So with this, we have done some evaluation here. If you take a look, like this is running on a 256 B100 GPUs on the Livermore Lassen system. And through any of this framework, like a DeepSpeed or Horovod or Torch Distributed, you go, we are able to give, in fact, almost 10,000 images per second faster training compared to using Nickel library. So here we are saying the MPI library can actually optimize all these collectives, whatever are needed for the DL and ML. So the MPI library should be good enough for people to actually get or extract higher performance. We are also working with application people here at Ohio State University. We are working with pathology department for a very concrete real case. As you know, the pathology, we go to hospitals, we give different kind of blood samples. Pathologists are able to very quickly find out what kind of diseases we have. But then it takes years for the pathologist to be experienced. So here the idea is that since the hospital has many of these slides, hundreds of millions, can we actually use deep learning on that? Okay? So this is the project we started. When they started in the beginning, their model was taking, they were only able to run it on a single GPU. It was taking 32 hours. And of course, that was not very productive. We worked with them team using model parallelism, hybrid parallelism. We are able to actually take it to reduce to 7.25 hours and then even reduce to 27 minutes. using 128 GPUs. So this was presented at SC20 last year, and soon you will be seeing like this kind of support being available. Similar things we are also trying to do with machine learning. We made a release of MPI for QML last year. You can actually download, and if you are using any of these machine learning algorithms like k-means, linear regression, nearest neighbor, and truncated SVD, or any of those other ones, you should be able to actually get even far better performance compared to the basic nickel support. For example, here we can give you like a 1.6x speed. Similar project also we have started with the DASC. Yesterday also you heard about that tutorial. So the DASC is for the data science. So currently the DASC support is only with UCX. We have introduced an MPI for DASC. We had a 0.1 release, and we made a second release 0.2, and now you can see using the MPI for DASC release, you should be able to get almost like a 6.9x better performance, or 3.47x for of the sum of QPy arrays. Actually, on all these websites, we have additional numbers. Please feel free to take a look at those. So moving forward, these are some of the features coming. I indicated earlier on the fly compression for only point-to-point communication. Of course, collectives can take advantage of it, but you can rethink to redesign all-to-all kind of very dense collectives using on-the-fly compression. So I'll show you some initial results, and especially as the model sizes are increasing, we have been exploring a lot of hybrid parallelism to take care of the out-of-core DNN models. And also the DL community is focusing a lot on the single image super resolution training. So these are some of our things which are being worked out. Here, these are some intermediate numbers. We are working on it. It is not yet released. It will be released in the next DDR release. So here you can see all-to-all operation with collective level on the fly compression. So now, based on the simple all-to-all, now we can reduce the time almost by 87%. Okay? So your all-to-all will be running very fast. Similar kind of things with the hybrid parallelism. We are trying to move into like a different kinds of model, transformer models. Here we show like compared to the basic data parallelism design, if we can have some hybrid parallel design, we have a scheme called Super that is like a subgraph parallelism, and here you can see we can give you almost a factor of 3 speed up. And in fact, tomorrow there is a talk by Arpan Jain. He will go into more details, and this paper was actually presented at the IPDPS this year. So then as this DL training is moving into the super resolution, like you have a single image, but you want to do the training with a very high resolution. So in this context, we have a paper here we presented at the IPDPS, and here again you can see the throughput, the basic nickel solution versus basic MPI, and we have done some optimization to our MPI library, and through that you can see almost you can get even 26% percentage improvement. So Quentin will also be presenting these details in the tomorrow's talk, and then this support will be available in the future MVAPICH. So then moving forward, the OSU Microbenchmarks, many of you are familiar with this. This is available since 2004. When we started the project, those of you who are not familiar, when we started the MVAPICH project, people knew how to evaluate application level performance, but people didn't know how to measure MPI level performance, like how to measure accurately MPI send, MPI receive, MPI collectives, those kind of. So we have been continuously working on this. Every time we have a new release, we actually have an OSU Microbenchmark. We started with MPI. We have a lot of Bcast things, CUDA-aware MPI, OpenACC. So these benchmarks are very widely used in the industry and a lot of procurement also. And in the last several releases, we have actually added even the ROCm support for evaluating the AMD GPU communication, and very latest release, we also added nickel support. So you can actually utilize OMB to have nickel level evaluation. And we are actually working both Python and Java binding MPI support for the OMB. So here is some early results. This is the OMB-Py. This is the CPU-based results. You can see that we are able to just evaluate like instead of a C program now to the Python. There's a Python, there's a big community. So how through those Python environments, you should be able to also evaluate the basic network level performance, like a latency, bandwidth, those kind of things. So this is the Python. With a very low overhead, with only 0.5 microsecond, we are able to provide these. And similar things we have also done for the GPU side. So here we have like a OMB-Py for QPy, NumPy, PyCUDA. Here we see some different kinds of overheads. So this will be available with the next OMB release. And in fact, tomorrow there is a short presentation by Neuron. He will go into more details on this. We are also continuing with our compilation of best practices. As you know, the MPI library has many parameters. If you go to this MVAPICH site, best practices over the years, we have a set of applications. People have been contributing. We encourage contributions from the community. If you have run this application with MVAPICH2 library with certain set of parameters, we will be happy to add this with credits to you so that the community can actually refer to these and get benefit. Yeah. So then in the last year, we have done a lot of work with the Stack community. As you know, that is becoming like a Stack is becoming like a the new package manager for people installing. So we have all the MVAPICH2, MVAPICH2X and MVAPICH2 GDR there. We have a detailed Stack-based installation user guide. And especially since MVAPICH2X and MVAPICH2 GDR are binary, we have worked with the Stack community very closely to see how to make those releases available. In fact, tomorrow there will be a talk from Todd Gamblin, he's the leader in the Stack, will be actually outlining some of those solutions. And over the years, I think we received a lot of requests. I think Adam Moody will be the next speaker. He has been suggesting a lot of these things from us in the earlier MUG meetings, and we have taken those challenges. So now in the latest releases, we have a lot of DL open things so that it removes the dependencies on libraries like IBverse, IBMAD, simplifies installation and deployment. These are already available in the latest MVAPICH2 releases, and we are trying to add more such functionalities so that in future, the installation will be even much more smoother. Now, we have been getting a lot of requests. We have, like as I said, we have the basic MVAPICH2, then we have the MVAPICH2X, and then MVAPICH2 GDR, and now we also have an MVAPICH2 AWS. So we want to unify again. Due to various reasons and all, we got within the group, we had to take care of those communities very quickly, but we are working on an integration plan. And in that case, it will be like under one umbrella, all these support will be available. So with this kind of thing, let me try to wind down. We have been like continuously looking for the Exascale systems. Some of these supports will be coming up very soon, like MPI tasks, tag matching, adapter memory, interlock 10, etc., etc. And while this is continuing, I also want to highlight, I think I mentioned this in the previous presentations, we have now a commercial spin-off, commercial support for all the MVAPICH2 high BD, high DL libraries. The support is being provided to several national laboratories and international HPC centers. But in addition to providing just the commercial support, now there is a lot of focus from this side on the value-added products. So tomorrow, in fact, there will be a talk from Exascale Solution, which will go into more details. And I think Gilad also indicated MVAPICH2 DPU. So those releases are coming through Exascale Solutions. Yesterday, we had a tutorial and live demo. We are also working with Livermore. There's a next product which is coming out called SCR Exa, scalable checkpoint restart for Exascale system. There is also an Exascale AI and Exascale HPC product. So here we are trying to, based on some of the requirements from some of the customers, they're also being aligned from the commercial angle. So with this, let me conclude my presentation here. I'd like to thank all the sponsors over the years, last 20 years, providing funding as well as equipment to make this project ongoing. But last but not the least, these are all my heroes. So what I presented here is a work of almost 70, 80 people over the last 20 years. So I'd like to acknowledge everybody's contribution here. So even though we have a big team, continuously our projects are being expanded. Since many of you people are attending from an international location here, I just want to advertise these. We have a lot of positions open. If you are interested in joining our group, and you would like your names to be added to that previous slide in a couple of years, please contact me. So with this, let me close here. And if there are any quick questions, I'll be very happy to answer. I have not looked at the Slack or the Q&A boxes. If there are any questions.
So there were a couple of questions. So one is, are there any plans or development for supporting RISC-V systems?
We have not gone into that. Many of these things totally depends on funding, because we are in an academia setting. So if there is a real need from somewhere, and if we can get the relevant funding and collaboration, we'll be very happy to explore those directions.
So our question master, Adam, had a question as well. So
sure.
He was asking if the sharp improvements available in MVAPICH2X already?
Yes. There is a basic support which is already available, and in the just as I said, like the MVAPICH2X, we are trying to make a release before MUG. We can do it. The next week, the release will have advanced support. Yeah. But we can give you even an earlier version if you want, for trying it out. Any other questions?
No, I think that was about it, Dr. Panda.
Okay, so thank you again. If you have any questions, this is my